prayed for. We prayed for the Criminal Investigations Project. There is a video going on. So you're going to watch it. Unbelievable. Yeah, usually I don't have students actually just do that. Usually they would skip the whole class, so I don't know. It's a little rude if you ask me. Okay. Well, he's definitely getting a 0 on the quiz, that's for sure. But anyway, getting back to this. What sorts of questions do you have about the homework? Were you good? Were you okay with this? Like, this was pretty easy, wasn't it? This first couple. Yeah, what do you got, Kelsey?
21.
Excellent. I wanted to do at least one of them, so thank you for picking that one. That was a good one, isn't it? So 21, sines and cosines, we love them. I'm just going to copy this so I can put it down at the bottom. Hold on a sec. There we are. Here we are. Done. Copy and delete. Okay. So let me pop this down at the very bottom of this so that I have room to write. So we're going to compute this line integral using the this thing. It's the same. I know it's got 3 instead of 2 components, but I think we can handle this. So let's go through this carefully. The first thing we're going to do is f of r of t. So f of r of t is going to be the sine of t cubed. Oh, yeah, what in the world? Plus the cosine of negative t squared plus t to the 4th. Sorry, I forgot my j. There. So I've just taken this for x, this for y, and this for z. And I think I got it all right, but let me know if I've got anything wrong there. Does this look okay? Okay, next I'm going to write down the derivatives. So the derivatives of x, y, and z. So this is going to be r prime. So this will be 3t squared times I minus 2t times j plus 1 times k. And now I'll do the dot product. And I set it up like this to try to clue us in to the fact that you're multiplying and then you add them up. So we're going to multiply these together, 3t squared times sine of t cubed minus 2t times cosine of negative t squared plus t to the 4th. And then all that's left is to set this up as an integral, and they were kind to us and made it so that even though it looks scary, it works out nicely. So this is 2t cosine of negative t squared plus t to the 4th dt. And the limits there are given to us, so it's not too bad. So let's just pound through this. I will sort of cheat a little bit, and I'll just mention that you're going to use this substitution here, and you're going to get the cosine of t cubed negative from that. And then I'll cheat a little bit here and say that you're going to use this substitution on this piece. And that's going to give us, let's see, that's going to be plus sine of negative t squared. I can actually write out the substitution if you need me to, like in great detail, but I don't feel like it if no one cares. And then there's that. And then, of course, limits. T goes from 0 to 1. And then the last bit, it's not quite as pretty as we would hope, but it's not terrible. We have the negative cosine of 1 plus the sine of negative 1 plus 1/5 minus, let's see, this will be the cosine of 0. The cosine of 0 we all know is 1, but that's negative of the cosine of 0. And then the sine of 0, we all know that is 0. And of course, 0 over 5. So let's combine all of this into one glorious answer. I guess it's 6/5 minus cosine of 1 plus sine of negative 1, which I suppose we could write that as the negative sine of 1 if we wanted to use the negative. I don't know. It's fine the way it is. Does that look all right? Is that the back of the book? It's got a back of the book, isn't it?
Yeah, that's
It's close enough. Yeah, they might have changed this sine of -1 to negative sine of 1 because of the negative angle identity there. All right, very nice. So that's working through the main thing, and we're going to be hammering this today because we're doing the fundamental theorem of calculus for line integrals. But the main thing is to note that when you're doing a line integral through a vector field, you compute the vector field evaluated on the curve, do the derivative of the curve, and then do the dot product. And after you do the dot product, no I, no j, no k, none of that. No I, j, or k. And then do the integral of this. But don't worry, you'll have plenty of chances to do it today because that's all we're doing. All right, anything else from this homework? This cleared things up? Now, the quiz is hopefully an easy version of this. No sines or cosines. It's just polynomials. So the only annoying thing will be having to square a binomial. But you can handle squaring a binomial, can't you? I think you can. Let's give it a go. There's 2. Here's 1. No. There's 2 for you. Here, I'll give you 1 more. Here, I'll put 1 here. The missing man. But, yeah, that's tricky. There's 2. There's 2 more. You don't want them? No. There's 2. There's something that's coming off in pairs today. I think there's 2 more there. Yeah. Papers, joy, happiness. All right, did everyone get a copy? No, good, good. Didn't know. We didn't know if there was a problem. I'll get my copy for the people watching, or rather for Daniel, because I'm sure he'll watch this later. Oh, I don't have limits. We can make up our, you want to do 0 to 1? Why don't I have limits on this? Yeah, 0 to 1. 0 to 100? You pick your own limits. No. Don't pick your own. Get all different answers. Yeah, let's do 0 to 1. Here we go. There. I got down to that place and I was like, wait, what are the limits? So here, you can use 0 to 1. Here. Hopefully. I'll grab homework first. Just for my stack. You're bored? Let me check my answers. YouTube not updated at all. If some of you are finishing up or done, you all set? Yeah. You have to get a box around it. Very nice. Yeah, it didn't come out to be quite as nice since I wasn't careful with my limits, so if If you get a fraction, you're probably right. You all set? Yeah. All right, good. Sounds like you're doing the right thing. Yeah, that's a good question. We have the meditative students. Let's do over it for a bit. It's fine. What do you think? You all set? You're not set. Wait, you don't have a. You're not going to put a box. You have numbers. You can plug in things, couldn't you? Let's see. You plugged in things. Very nice. You plug things in. Very nice. Oh, you've got a correction. Good job. You got a fraction there?
No, I didn't.
Oh, you do? Oh, you just didn't want to simplify.
Yeah.
But it is a fraction. I mean, if you added all those numbers together.
But maybe.
Like, all of the zeros, wouldn't they just be zero?
Yeah. Well, I plugged them in just so you can see what I'm doing.
Okay. You got something? Good job.
Do you want me to simplify it?
Oh, you got your little pile over here? Wait, Katie, you're traditionally the last person. I'm not going to do this.
I do it.
I know, Josh, but you want me to look. Oh, wait. You had it. Okay, he's getting his fractions.
Yeah.
Oh, you got yours still? Oh. You got a fraction.
Yeah.
Hey, what's so fun about that?
I don't know.
I don't see anything funny.
It's a fraction.
Okay, now I've got them all, right? Including the meditative students. Okay. Yeah, so everyone got nice fractions, just that they weren't all the same fraction. So, so check my work, because I did match up with several of you, but not all of you. In fact, a very small minority of you. So let's double check to see. I did, first of all, f of r of t. So I plugged in x is 3t here, and y is this thing there. So I got 3 times 3t times 4t. That's this, and then this is 2 times this squared plus or minus this thing squared. Wait, where did I put? Oh, I didn't put the square there, but I did square it because I remember squaring it. Let me put the square there. So I've got my notation is bad there. Oh no, yeah, that's this squared. Yeah, I remember thinking I'm going to square that, and I did square it down here. Okay, so then I did the derivative of this. So that's a 3. I should have picked better. I don't know. I pulled this out of my files, to be honest. I didn't make this one up this morning. Had I made it up this morning, I probably would have picked simpler functions. The derivative of this is here. And then I multiplied this times this and got this. Okay, so just so that you know what's what. This stuff, that stuff came from this times this. So you can double check my math. For example, 3 times 3t times 4t squared times 3 is 108t cubed. And 3 times 3t times 2 times 3 is 54t. So I think I got those right. And then this one was more challenging, but I was arrogant and did it in my head. But I think I got it right. So this is all of this stuff times this, and I squared the binomial and got all of this. So hopefully I got all of that right. Let's just assume I did for now. I'll double check on my computer later. But anyway, then I got this. So basically I combined like terms. So for example, the 32t and the 54t. So 54 minus 32 is negative, or is positive 22. And then I combined all the cubes. There's this one, and that one. 124t cubed. And then didn't have to do anything with that. Got my antiderivative, plugged in 0 and 1, and I got this. So, okay, there's a few of you. So I'm hoping, I'm double checking though, because even though there's only a few celebrants out there, I'll double check on my computer before I grade this and make sure that I got it right. For now we need to move on. I guess I spent my time trying to come up with good examples for the fundamental theorem of calculus for line integrals. So I should have used this problem for the quiz because this is far easier. So why don't we practice again with this problem just to see. You know what? Before we do this, I need to mention something. Just a quick intermission. We do have end of course surveys that are open today. They're open for 2 weeks, and you can fill them out. Just so you know, the administration cares very deeply about the numbers. I care very deeply about the written stuff. So if you answer the numbers, fine. But if you write something like a little secret note, they're anonymous unless you put your name. Some people will put their name like, "Hey, it's me," or whatever. I get some interesting comments just because I don't know why. Some people decide to make comments about my choice of shoes or whatever. But anyway, so do fill out those surveys. You will be getting extra credit for doing it. It's a small extra credit, like the equivalent to a quiz grade, but it's something. So I'll make sure that you get that extra credit. I can tell who has filled out the survey. I can't tell what you said. So just so you know, I just know who did it. So if you're concerned that you won't know the answers to the survey, I'll just help you out here. Here is the correct answer. You can use that for all of the answers. 5-star reviews. I always like 5-star reviews. So let's get back to this. We're going to go ahead and do this. So we'll work through this one together. And then I've got a couple more of these. And then you can guess what's going to happen is I will reveal to you the fundamental theorem of calculus, which will make it all so much easier. But for now, let's just go ahead and try this. And I need to pick a random person, so I'll do attendance. Come on. Oh, come on. Okay. Okay. Thank you. Submit. Okay. All right, so I've finally did my attendance. So let us randomize. Oh, of course, the first person isn't here, but we can do. Kelsey, what's the first thing you're going to do to compute this line integral?
The first thing I do is plug R of t into F and make everything into roots of t.
Okay. Very nice. So we're going to plug this stuff in. This is my x, this is my y. So this will be, let's see, 2 times 5 minus 2, 5t minus 2. You know, this is so ugly. I'm gonna regret doing this on here. So I'm going to just switch over to where I can actually write. Now copy and delete. Give me a sec here. I'll do the same thing with the future ones. So we have like four of these to do. Okay, so we have f. Oh, come on. Try again. F of r of t. Very nice. So this is going to be 2 times 5t minus 2 times 1 times I plus 5t minus 2 squared times j. Okay, so far so good. Next volunteer. Matthew, what's the next thing that you're going to do?
The derivative of
All right, what is that derivative?
5i plus 0j.
All right, so 5i plus 0j. Beautiful. Okay, we're almost there. Next volunteer, not here to do it, but I know he could. Christopher, what's next on the agenda? All right, yeah, dot product these things. F dotted with R prime. And notice that since this 0 is here, we're not going to have to worry about squaring that binomial. So you could if you want to, but it's going to be multiplied by 0, so why bother? So let's see if I can get this. This is going to be 50 times t minus 2 times 2 times 5, 20. Does that look all right? Okay, so now we've got all that. Let's set it all up. I guess the rest of it is pretty straightforward. We're going to do the integral from 0 to 1 of 50t minus 20 time dt. So this will be 50t squared over 2 minus 20t evaluated from 0 to 1. So what's that? 25t squared minus 20t? 0 to 1. Have I done it all correct so far? So is that a 5? That is a 5. Well, I guess that makes sense since I just told you that if you don't know the answers, you could always just use 5. So excellent. We got it. We got the first one. We got the first one right. So the right answer here, of course, is 5. Just stick that in your head and keep it there. Okay, so that's the first one. Now, there's an interesting thing about this that we're going to discover with this next one. The next one, it's the exact same function, but it's a different curve. So see if you can work this one out. I'm going to just copy this so that we can see it with its friend. Copy. Give me a sec. I'm going to move this over here and paste this in here. So you'll notice it's the same vector field, different curve, same vector field. So that's the difference here. So we're going to do the same things that we did just a minute ago. So what do we got here? You said do f of r of t. I'm already regretting choosing this. Okay, so let's see. This is going to be 2 times negative 5 halves cosine plus 1 half times 5 halves sine, man, plus 1. Okay, surely I can simplify this at some point. And then we're going to add to this x squared. Oh, okay, 5 halves. It felt like a good idea at the time. Okay, well, and that's going to be squared times j. Wow, that's so nasty. Okay, I may resort to using a computer for this. I really didn't think it would be this ugly, but I didn't think through carefully enough. Okay, that's all right. We'll use the computer. We'll use the computer for this one. But we do need to set up the integral, and then we'll just cheat and use the computer. You could always cheat and use your calculator as well. You know how to do that. But I'll do it on the computer. R prime, we need to do R prime, and this is something you can do, I'm sure. So let me find some volunteers to do r prime. Tyler, what is the derivative of the x component for this thing?
5/2 sine t.
Nice, sine of t, and that's times I. Okay, very good. And then Luke, what about the derivative of the second component there?
Make 5/2 cosine t.
So you said 5/2 cosine of t times j. Very nice. So derivative. So Tyler noticed that the derivative of cosine is the negative sign. So put that negative in there, and double negative makes a positive. And then we had the derivative of sine is cosine. Okay, so far so good. Now let's just put this all together with a dot product. Okay, let's see. It's going to be 2. Oh, here. I will combine a few things, but not much. So this is f dotted with dr. So we have 5 sine of t. So cancel the 2 times this nasty thing. Cosine plus 1/2. 5 halves sine of t plus 1. Ugh. Okay, plus this will be 5 halves cosine of t times negative 5 halves cosine of t plus 1/2 quantity squared. Wow. It looked innocent, to be honest, when I'll show you why in just a minute. So this will be the integral from 0 to pi of that dt. I'll do this on the computer while you're doing the next one. So we got a third one. Don't worry. Hopefully this one will be a little bit less bad. Let's see, what is the next one? That one. It's this one. That's pretty ugly. Give it a go, though. Yeah, you work on this. I'll at least get it set up. Get it set up. This one, at least it's polynomials, right? Yeah, we got to get this fundamental theorem ready, because it's going to save all the time that we're about to do. There it is. Okay, and meanwhile, I will do, here, I'll just freeze this. That way I can see. I'll type this in. So if you get it set up for me, I'll type it in and do it. Okay, so give me a sec. I'm going to type in this one that I have here. There it is. Make it big so you can see. I got it. Okay, I'm ready. I'm ready for your for this next one. Okay, let's get it there. Hopefully this one isn't as bad. I've got the answer. I'll show you in just a minute what the answer is. So let's see if we can work this one out. We've got f of r of t. Is this really super bad? Let's see, 5t squared minus 2, multiplying a binomial by a trinomial. Well, binomial squared isn't that bad, is it? 5t squared minus 2 squared. Do I have this correct so far? F of r? And then we'll do r prime. Oh, r prime is better, isn't it? Because you've got 10t times I, 2t minus 1 times j. So f dotted with dr, 20t 5t squared minus 2t squared minus t plus 1 2t minus 1 5t squared minus 2 squared. Yeah, I guess that's it. Okay, so this is the integral from 0 to 1 of that thing dt. Huh. Yeah, I guess that, I mean, it's doable though. You could do it. It's not like the sines and cosines where you're going to have sine squared and cosine cubed and all of that mess. Okay, so let me show you the answer to the previous one. Well, I'll get this one in just a minute. We got to do them all. But actually, we don't have to do them all. There's a fourth one that we're definitely not going to do. So let's just back up to this one because you might be curious, what's the answer to this? Well, I've got it here. I'll show it to you. Let me make it big so you can all enjoy the answer. You could probably guess what the answer is, but there it is, right there. It is 5. I just wanted to reinforce, just so you'd know what the right answers are. So that one is 5. So let's put it up here. 5, 5. Okay, let's do this one. Let's see if I can type this in without seeing it. It'll just take a sec. You could do this on your favorite computer algebra system, Desmos or whatever. I just happen to have this installed on my computer. I'm used to the syntax, so I'm going to do it like this on Maple, this ancient. So let's see, what's 20 times t. I think you can probably guess what the answer is. Minus 2 times t squared minus t plus 1. Oh, I have an I there that shouldn't be there. Let's see, 2 times t plus minus 1 times 5 times t squared minus 2 squared. And I'm going to do t goes from 0 to 1. All right. Oh, look, what a surprise. The answer is 5 for that one as well. So what I wanted to show you about these is this, that you have 3 different line integrals through the same vector field. So here's the situation that we're looking at. We have these three line integrals through this vector field, and each one of them starts and ends at the same place. Let me just show you this. Here, this is a nice straight line. That one's the easiest to figure out. So that one starts at, let's see, if you plug t equals 0 into that, you get negative 2, comma 1. Sorry about my negative 2. And it ends at the point 3, comma 1. So if you plug 1 into that, you get 3. So if I drew this on a graph, I start over here at negative 2, 1, and end at 3, 1. So there is path number 1 through this vector field. Path number 2, this one, it starts, as you might guess, at negative 2, comma 1. It ends at 3, comma 1. I thought that this would be a fun one to do, but I was wrong. It follows a semicircular path, hence the sines and cosines. There you go. The third one that we just did, it's a parabolic path. And honestly, I haven't graphed this. I suppose I could graph it since I have this booted up here. Just a sec. I'll put it on here. That way we can see what it looks like. So let's go ahead and plot this. Let's see. What's the first component? 5 times t squared minus 2. And then the second component is t squared minus t plus 1. Whoops. And t is going to go from 0 to 1. How about that? Will that work for me? Oh, it did. So you have this, you can't see it, but I will make it visible once I get my arrow to be, oh, it's invisible, my invisible arrow. Come on. Oh, annoying. Yeah, I've been having trouble. And so here, I'll just shrink it. But there it is. There's the path. You can see it's this, well, it's not parabolic, I guess. It's what is it called? It's a quadratic in both x and y, so it ends up being something weird like this. Okay, yeah, there's the idea. But the important thing about all 3 of these paths is all of them start and end at the same place. Now, when you have a path that starts and ends at the same place, if you have a special vector field, which I'll explain what I mean by special, you'll always end up with the same answer for the line integral. And so, as you might guess, this last, where is it? Where's my last one? I thought that this would be the worst, and this is the one that I was going to say, let's not do it, but I should have said that about the other one. This one, if you plug in 0 to t equals 0, you start at the point -2, 1. And if you plug pi over 2 into this for t, you find that you end at 3, 1. But the path is some crazy path with sines and cosines. I don't know what it looks like, to be honest. It might, here, let me get back here. It might do something like this. I don't know. But it's some path that starts over there on the left, ends at the right. And so what we'll do is, instead of using the calculus that we've learned, we're going to apply the fundamental theorem of calculus for line integrals. Now, you know what the fundamental theorem of calculus says for Calc 1. Fundamental theorem of calculus says this, that if you have a derivative and you do the integral of a derivative, you get the from a to b, you get the function evaluated at b and evaluated at a. So if you know what function, the antiderivative, you can just do this, and you can avoid doing the hard work of doing a Riemann sum. So that it looks sort of similar when you do the fundamental theorem of calculus for line integrals. So the fundamental theorem of line integrals is it's sometimes called the fundamental theorem of calculus for gradient fields. So this is what's special about the field that I had, is it's a gradient field. I'll explain how you're going to know whether you have a gradient field or not in just a minute. But if you have a gradient field, then all you have to do is figure out what function this field is the gradient for. So let me back up to the field. So just to show you how this works, the vector field that we just worked with is this. And this happens to be the gradient of a specific function of two variables. Now, you know what the gradient is, don't you? The gradient is the derivative in the x direction and the derivative in the y direction. So if you know that this is the gradient of some function, can you guess what the function is? I'll explain how to figure it out in just a minute, but you probably can guess. Like looking at this. This is the derivative with respect to x of a function. This is the derivative with respect to y of the same function. So what's the function? Anyone want to guess? You got it?
X squared y.
Yeah, x squared y. X squared y, derivative in the x direction is 2xy. X squared y, derivative in the y direction, x squared. Very nice, x squared y. So what this tells me is, if this is true, which it is, this is the fundamental theorem of calculus for line integrals, instead of doing the line integral the way we've learned, if you have a gradient vector field, then you can use the original function and just basically apply that original function to the start and end point the way you would back in Calc 1 when you're doing a definite integral. So just backing up, let's just back up one slide, back up to here. So this one, you'll notice that this is that gradient vector field. And so the gradient of f, little f, is this vector field, where little f is x squared y. And so in order to compute this line integral, all I have to do is plug the endpoints of the curve into that original function. So let's find the endpoints. R of a, which, well, here, I'll just write it as 0 because it's r of 0. So a here is 0. We're starting at 0. So r of 0 is the point. Let's see, it's 3 times the sine of 0, but we all know that the sine of 0 is 0. Minus 2 times the cosine of 0. The cosine of 0 is 1. So that'll be negative 2i. And then the cosine of 0 is 1. So I'll just 1j. So that's the starting point. So we're going to plug negative 2 and 1 into this in just a minute. And then the end point, r of pi over 2, is, let's see, 3 times the sine of pi over 2. Pi over 2 is a right angle. Sine of pi over 2 is 1. Minus 2 times the cosine of pi over 2, that's 0. So 3 times 1 minus 2 times 0 is just 3. And then cosine of 4 times pi over 2. 4 times pi over 2 is 2 pi. Cosine of 2 pi is 1. So 1j. So that corresponds with this point. So all I need to do is compute f of 3, 1 and subtract off f of negative 2, 1. And that gives me the final answer. Let's see, 3 and 1, that's 9, minus negative 2 and 1, that'll be 4. And sure enough, as we know, the answer is always 5, at least for today, because we're dealing with the fundamental theorem of calculus for line integrals. It doesn't matter how you get from this point to that point. Whatever curve you follow, you're going to have, it's going to be the same exact integral. Okay, so I guess the main thing that we need to deal with now is how do we figure out this little f. So let's go back to PowerPoint land just for a minute. So in order to find that gradient, oh, I deleted that slide. Oh, well, I edited this, and apparently I deleted the slide. So we'll just do it on here. So if you're given f of xy, how do you know if it is a gradient vector field? So let's just, let's do it like this. I'll do this. Sine of x I plus cosine of y times j. Let's try this. Is this a gradient vector field? Here's how you tell. What you're going to do is you're going to do the derivative of, let's see, we'll call this p and this one q. So you're going to do the derivative of p with respect to y, and you're going to compare it to the derivative of q with respect to x. So I know this is it's a little bit confusing because what you're going to do is you're going to take the derivative of this, do it with respect to y, even though this is in the x component sort of thing, and you do the derivative of this thing with respect to x. The reason for this is because we know that the mixed second partial derivative is the same no matter how you do it, and so this is the derivative of the original function with respect to x. So we're going to take that, do the derivative with respect to y, and do the derivative of this with respect to x. So that's how this is going to shake out. So we need some people to do these derivatives for me. So I'll get someone here. You go ahead and do your derivatives as well. Oh, you're not here, but you would do it. Fine, Claire can do it. Claire, take that first one, p. What's the derivative of this with respect to y? Oh, it's 0. Yes, it is 0, isn't it? All right, Andrew, what about the derivative of q, this thing, with respect to x? Oh, it's also 0. Now, if these things are the same, then you're happy because this is a gradient vector field. It's what we call a conservative vector field. You remember we talked about conservative vector fields, just the idea of conservation of mass, conservation of energy, all those conservation things. All of those things would be gradient vector fields. So if you take gravity, gravity is a conservative vector field. Anyway, getting back to this, now we just have to figure out what is little f. So here's how I find little f. To find little f, what I do is I find the integral of p with respect to x. Hold on a sec. There we go. So maybe I should put little f here. So this isn't the answer yet. So I do the integral of p. So basically I'm going to say this is the derivative with respect to x of some function. So let's find out what that function is. This is the derivative with respect to y of some function. So I find the derivative with respect to x, and then I find the derivative of the other one with respect to y. And then what I do is I combine the two. Whoops, I combine. Now we'll have to deal with how to combine in just a minute, but let's just do these. This one's not bad. So I know you can do this. Joshua, you know what the antiderivative of sine of x is, don't you? It is negative cosine of x. Very nice. And Briar, you know what the antiderivative of cosine of y is, don't you? Just sine of x, or of y, sorry. Sine of y. Now, the way you combine these is I do what I think of, at least in my head, I think of doing a union. You know what a union is, right? If I take the union of this class with my 8 o'clock class, everyone here and everyone in my 8 o'clock class would be in that group. And it just so happens that Cooper here is in both groups, but there's not going to be two Coopers running around. There's only one of him. So Cooper Stiegel here. Or Stiegel? What?
Stiegel, like eagle.
Yeah, that's the way I've tried to pronounce it, but then I doubt myself. But anyway, so Cooper, there's only one Cooper Stiegel in that group. So the same thing goes here. If I combine these by doing a union, I want to have everything here and everything here, but I don't want any duplicates. If there's a duplicate, I don't write it down. Fortunately for us, there is no duplicate. There's no overlap. So this, my f, is just going to be negative cosine of x plus sine of y. And that's it. Let me just do one more of these just to see how this works. And then I think we'll just have to call it a day, maybe. Okay, so let's say that I have this vector field, f of xy is equal, since I deleted that slide, I need to think about this for just a minute. So we're going to go with 2xy squared plus 3x, that's good, times I, and then 2x squared y minus 3y squared. We'll use that for j. There it is. Okay, so we're going to do, remember, we have to first of all check to see if this is a gradient vector field or conservative, if you want to use that type of term. And that's not a political term. It's like conservation of energy, conservation of mass, those sorts of things. So it's conservative, but we want to check first. So the first thing you're going to do is you're going to do derivatives. So I'm going to do the derivative with respect to y of the x term and the derivative with respect to x of the y term. So let's see if that works out. And then as long as those are equal, then we're going to do our math. So we'll start with Madison. What do you think of the derivative with respect to y of that first thing? 4xy, very nice. And then Rachel P., what about the derivative with respect to x of that second thing? 4xy. Same. Hey, they're the same. So when they're the same, we are happy because this is conservative, or rather it's the gradient vector field. So now we have to figure out the actual function that results in this gradient vector field. So I'm going to have to do the integral of 2xy squared plus 3x with respect to x, and then I'll do the integral of the other one, 2x squared y plus, or is it minus? It's minus. Hold on a sec. 3y squared with respect to y. So do those two, and then we'll combine. Okay, we can do this. We're almost there. All right, you can probably do this on the fly. So Rachel J., what do you think of the first one? What's the integral with respect to x of that thing? We have x squared. That's beautiful. All right, Emily, what about that second one? What's the antiderivative of that with respect to y?
X squared, y squared minus y cubed.
All right, beautiful. So remember, combining, think of it like a union. You're unioning these together. We don't need both of these. We just need one of them. So we'll just pick one. Well, they're the same. So put one of those down there. So x squared, y squared. One way you could do this is you could say, okay, check that off, check that off. We've got those. Now we need to have plus 3 halves x squared. Now this is the derivative with respect to x will be happy. And then we need to make the derivative with respect to y happy, so I'll throw that in there. Check that one off. Done. Now everyone will be happy. That is the combined function. And if you do the gradient of this, you actually get that up there. So that's how you're going to figure out your function. So then to put it all together, whenever you have the integral of f dotted with dr, if f is a gradient vector field and the curve is anything, then you just have to worry about the start and end of the curve and plug them into here. So just as an example, let's just suppose that the start, since I don't have my slides, they disappeared. The start is the point 0, 0, and the end is the point 1, 1. And just so that you know, the curve that I'm thinking of is this, starting here at 0, 0, ending at 1, 1, and it's this one, the curly Q. We're going around in little loops. There it is. So there's the curve, but we don't care. We don't care what the curve looks like. We just care where we start and where we end. And so this would just be the function value evaluated at 1, 1 minus the function value evaluated at 0, 0, which in our case is just going to equal 3 halves. So you can plug those in if you don't believe me, and you will get 3 halves. Okay, so the homework for tonight is hopefully we've covered everything we need to. If not, I guess we'll deal with it tomorrow. I'm going to stop the recording.